Good afternoon. Today we're talking about our capstone project, which is a combined electromagnetic and pressurized high-velocity projectile launcher as a proof of concept for a fully integrated model-based systems engineering design process. So we're Team Spud Buds. I'm Dana Sanders.
I'm Lauren Cherry.
Sam Ortega. Marco Esponvilla.
And our project mentor is Michael Hardigan of APL.
Our agenda today will be talking about our project scope, our sponsor, overview, and value. Our project framework, which consists of foundational concepts, predictive equations, and our physical architecture, and our project procedure, which is our control interface and our data analytics.
So I'm going to talk about our project scope. First off, I'd like to give a little bit of background about our sponsor, which is the Johns Hopkins Applied Physics Laboratory. It's actually where I had my summer internship for the past 2 summers, and where I will be going on to work full-time after I graduate. So APL, as it's known, was created in 1942 to help the Allied war effort during World War II. They did this specifically by designing the BP fuse, and it's a fuse that was attached to our missiles to trigger them to explode when in proximity of overhead aircraft rather than having to hit them straight on. That really helped in the war effort. And So APL supports a wide range of governmental agencies, including the DoD and all of our military branches, NASA, the Department of Homeland Security, and others with a very broad range of technical expertise that covers basically the entire breadth of our STEM fields. And it's also the largest UARC, which is the University-Affiliated Research Center in the country. We have, last time I checked, over 6,700 employees in Laurel, Maryland. And APL has been a part of the Fleet Ballistic Missile Strategic Weapons System program since 1955. And our mentor, Mike Hardigan, is one of my direct task leads. He is also one of the design leads for the Trident Missile program at APL.
So as an overview, our project uses model-based systems engineering principles with the integration of hardware in the loop simulation. To model ongoing APL project development without using any classified data, we chose a projectile launcher that will provide similar experimental output. The model-based systems engineering tool, Magic Draw, has played a key role in the design of the project and will also function as a control interface for the firing procedure. The main purpose of our project was provided by APL's Michael Hardigan, who requested that we demonstrate the capability to integrate Magic Draw with hardware in the loop simulation. Both APL and the Navy are shifting away from document-based design work to model-based, and because this process is ongoing, APL is seeking out new capabilities for the Magic Draw tool. With this demonstration, we can provide evidence that there is value in this testing methodology for the Trident program.
So for the project framework, we have 2 foundational concepts. As Marco stated, APL uses MBSE and HWIL. So MBSE is model-based system engineering. This is the application for modeling a project to support the systems engineering. This process is done through Magic Draw, which is a graphical interface to help communicate decisions of the project's components. And then hardware in the loop allows simultaneous testing while the system is still in the design phase. So the purpose of that is to discover the main weak points of the project before it gets manufactured. That'll just help look at all the failures within the project, and then you can go back into the system, Magic Draw, looking at the failures, redesigning them, reworking them out to prevent future manufacturing implementation.
All right, so for the projectile launcher itself, we'll be considering the projectile to be affected by magnetic forces, drag forces throughout its course through the launch, and we'll be experimentally figuring out the pressure and velocity relationships between the pressurized portion of our projectile launcher and the velocity of the projectile itself. We'll model this through differential equations that will target and predict where the projectile launcher will land depending on air and the other forces that we have studied. Slide. We'll be doing this through analytical modeling techniques, implementing the differential equation in some code that will take time derivatives of the course of the launch itself so we can predict where the projectile will land.
This is a magic diagram. It's based on block diagrams that some of you might have seen in the past. So each of these blocks represent a component of our projectile launcher. Our main components are the Arduino, which functions basically as the main control of the projectile launcher. Then we have our launch tube and our launch frame, and then our compressor with its air tank. Here, these yellow boxes here and here, these represent control flows from our Arduino. Our Arduino will be linked through MATLAB, which will then be linked into MagicDraw, so that we could input control signals and have, say, for our stepper motor, this will control the firing angle of our projectile launcher. So we'll be able to enter an angle that we desire in MagicDraw, and that will lift the projectile launch tube to the angle that we specify. And then when we press the fire button, basically, MagicDraw will trigger the release valve to open, and that will launch our projectile. Then with the green boxes, so here and here, this represents the flow of data. So this is as our experiment happens, our two sensors, the velocity transducer and the pressure transducer, will send their experimental data back through the Arduino into MATLAB and then into MagicDraw, where MagicDraw will be able to conduct comparative studies based on the experimental data against our predictive equation results.
So this is an inventor drawing of our structural frame. The middle beam is used for stability and will have a stepper motor on it, which will be wired to the PVC pipe with a belt to rotate the angle of fire. The air compressor and tank will be inside the base of the frame. This is our actual manufactured frame. In this photo, we were in the process of getting all the components, but in the background you can see our PVC pipe and the air compressor. And then we later went on to cut the PVC pipe. If additional stability is needed, we plan to add sandbags to weigh down the frame.
So our projectile launcher will have an onboard sensor suite. This will consist of two pressure transmitters. One will be in the tank of the compressor because the tank comes with one, but it's one of the needle gauges and it's not very reliable. So we'll have one there, and then we'll also have one in the pressurized section of our projectile launcher, and that will feed data back through MagicDraw, back through the Arduino into MagicDraw for our comparative study. We'll also have, not pictured here, but we'll have a set of photoelectric speed sensors. So they're paired sensors of a laser diode and a photodiode that it's aimed at. So as the projectile is fired, it'll pass through the laser beam, and there'll be two of them. So as it passes through, it'll measure how long it takes for it to pass from 1 to the second, and we can use that to calculate the speed of the projectile. And then this is an anemometer. So it measures wind speed and wind direction. We'll be using that to take live test data on site as we perform our experiments, and then we'll be able to record that in MagicDraw as we perform our experiments to use in our predictive equations. All right. So I'm going to go into our project procedure right now. This is an activity diagram in MagicDraw. This is, excuse me, it shows the three main phases of our proposed experimental procedure. We have the priming phase, the firing phase, and then the post-firing phase. In the priming phase, we will do things like we'll pressurize the tank to build up pressure because it takes a little bit. We'll input our desired firing angle in MagicDraw, as well as we will input or record our wind data in MagicDraw from our anemometer. And then once we enter the firing phase, things will happen simultaneously. We will hit the fire button, launch the projectile, and at that same moment, it will use the data we've inputted to compute the results of our predictive equations. We'll have our pressure, our angle, and our wind velocity and other wind data. So afterwards, once the projectile is landed, we're in the post-firing phase, we will be manually gathering data points. That's just how far did it go. We'll measure the distance from where the projectile was fired from to where it landed. And once we've done that, we will input that also into Magic Draw, and we can run a comparative study between the two values.
This graphic represents APL's Trident missile. This missile is a submarine-launched ballistic missile, which is armed with thermonuclear warheads. So our project is being modeled after this. However, we are not going to throw thermonuclear warheads on our project. So therefore, we are doing a very simplified version of the modeling the Trident missile. Okay, as stated before, we will get the predictive equations from Magic Draw. We'll get the pressure, velocity, and the distance at 3 different angles, 30, 45, and 60 at 3 different trials. And once we have our predictive equations, we're going to actually fire our projectile launcher, get our actual ones, and then we'll be able to compare the predictive versus the actual data. We're planning on getting the data throughout the month of November, so we will be prepared for our final presentation in December. Any questions?